Okay. Let's go ahead and get started. Pull this out of the way. Sorry. A little delayed today. Wanted to make sure, anyone who was running late had a chance to get here. Okay, so today we're going to be primarily talking about testing and automated testing and how you can run automated tests and how you build them and what you should and should not do with automated tests. At the very end of class today, I'm planning on us ending a little bit early so that if anyone has questions about Swift data, which we covered previously, they can ask. Just because Swift data is very complicated and very painful and difficult to use compared to everything else we've done in Swift so far. But today, for now, for this part, we're going to talk about automated testing, right? So, automated testing. Specifically, the first thing we're going to talk about are unit tests. Unit tests are a form of automated testing. There are primarily kind of 3 different forms of automated testing that we'll talk about today. Unit tests are the first. So, what is a unit test? A unit test is a special piece of code that runs other code, okay? So, when you write a unit test, you write it to make sure that other code that you've written does what you think it will do. It lets you check the values returned from functions or methods that are on your types that you've created, right? So if you've created a function that, I don't know, transforms data in a particular way, and it might have some complicated state to it where, sometimes it does it this way and other times it does it that way, and it's not super obvious how it works, you can write a unit test to very quickly send stuff to that function, get stuff back, and then make sure that it is what you expect that it should be, right? And you do unit tests, as I was saying, typically you do them one function at a time. So rather than, testing an entire set of functions, all at once, or you're, putting an entire class or struct under test, usually each unit test that you create will exercise or run the code of one function. Now, the particularities of what that looks like in Swift testing mean that it's going to look like you're running a lot of different functions all at once, but don't worry, you're not. Because Swift testing just makes things easier and reduce boilerplate, which is nice. So you put the data in, you get the data out, and then you check the data. That's really all a unit test is. Sending something into the box, getting something back from the box, and then saying, is this what I thought it would be? Is this the, right, the meme? I should have put that meme in here, right? The guy with the butterfly, in the Japanese textbook. You guys know what I'm talking about? Okay, never mind. Anyway, so yeah, and I hit the button that went all the way back. There we go. Unit tests are the lowest layer of testing that we're going to look at. So they are the tests that are the closest to your code, to your pure code. We're going to look at 3 different kinds of tests, and this is the kind that's the closest to your code, and therefore, in many ways, the most useful kind of test, if written correctly. So let's take a look. This is what a unit test looks like with the Swift testing framework. So the most basic kind of test that you can write is a function with an @test macro placed in front of it to tell the compiler, hey, this function is for testing specifically. All test functions in Swift testing can be written as if they are async, and they can be written as if they throw. But when Swift testing runs these functions, if you throw from the function, then rather than crashing your program or anything like that, Swift testing catches it and just flags the test as failed, okay? And a big part of what you're doing with unit tests is making it so that you have a lot of tests set up covering a lot of your code, and then you can go in and change your code and then run tests to make sure everything still works the way that you expect it to. So it makes it safe for you to refactor and change your code. And then you can be secure in the knowledge that you haven't broken something with your changes. Okay? So, most basic kind of test. Oh, and then of course there's the hashtag expect macro. That is the actual unit test right there. The function itself is kind of more of a wrapper around the ability to use the hashtag expect macro. But hashtag expect is basically the unit test. You pass it a Boolean value. The Boolean value is either true or false. If it's true, the test passes. If it's false, the test fails. So here we have an expression which evaluates to a Boolean value. Now, in this case, assuming that you're not building on a quantum computer that has unstable qubits or something like that, we know that this will always pass because 1 plus 1 is always 2, usually. So, what do we use them for? I think I kind of already covered this a little bit, but we use them to validate our assumptions. We use them to make sure that what we assume about our code is true, where we look at our code and we're like, yeah, I'm pretty sure if I pass in, this string or this number, then this will happen, right? Tests make sure that that's true, right? They check values returned against what we expect, right? So they basically allow us to say, I have this expectation, and then compare that to what actually comes back from the test, or from the function, right? Again, a lot of this is stuff that you primarily do right now manually. You're going to be running your application, and then pulling it up, wait for it to load, wait for it to compile, wait for it to build, wait for it to load, put it on your phone, or simulator, or in the preview, right? Preview's so much faster, right, than those previous two. We didn't have preview when I was learning, okay? But that said, the preview has limitations. So unit tests are still very, very helpful. Yeah, so basically you're doing a lot of this all yourself already. This just makes it so you don't have to do as much of that, right? So yeah, check your values returned against what you expect. They verified our error handling. So if we have a way to specifically handle errors where we need to throw a particular error or we want to return a particular value whenever there is an error, we can pass in information that we expect to cause an error and then have an expectation macro set up on the outside where we say, hey, is what we got back an error, or did what we get back throw the correct error, the one that we expected? If so, cool, the test passes. Yeah, got ahead of myself again. The other thing is that's really nice about unit tests is typically, especially as a part of an automated build process where you're trying to deploy things in production as you do in the professional space, rather than running the entire test suite all at once, there's a cute little play button, and we'll see this in part 2 today. But there's a cute little play button right next to every single test. And you just click that, and it will immediately build, run, and execute just that function. What this means is that if you have hard to reach code in your app, if you have a detail view inside of a list, inside of a list, inside of a list that's inside of a search, and whenever you want to test that view, you have to do all that stuff either on your phone or in the preview, right? You can instead write a function around that piece of code that's a test, that's marked at test, and then you can run that test, and you can basically check to make sure that it works correctly in less than a second, which is much faster than spinning up the app or starting or building the preview and testing the function that way. So, cool. So let's take a look. This is an actual test, one that's not testing something that is axiomatically true, but this is how you would write a test for, okay, slow down. I did not tell you to go that far. Go back. Back one more. Here we go. Okay. This is how you would write a test for a single function. So we have our addition function here. You might recognize something like this from back when we were doing the calculator application on the command line way back when. You guys remember that? That was over a month ago. Good times, good times. Anyway, back then, you know, we didn't have a way to really make sure that this worked except for run the application and pull up the command line from it and type in your numbers, and then it would do the thing, right? Here, you can instead just run this test immediately, and it will tell you whether or not it's true, and whether or not it works correctly. Okay, so here you can basically pass in information, get back information, and then validate that it's what you expect it would be. Now we can go forward slides. Thank you. Okay. Within a single test function, a single @test function, you can have multiple different expectations. So you can set #expect multiple times. And what happens is, even if one of those #expects fails, the function will continue to run, and it will check every single one within the function and make sure that it all works correctly. Okay? So, for example, here, we could, if we wanted to, add another expectation where we're testing the subtraction function, right? And we're making sure that 10 minus 5 does in fact equal 5 according to our function, right? And what it does. You know, what the subtraction function is actually doing up here is less important. We don't technically need to know that in order to write this test. And that's something that's kind of going to be key a little bit later on when we talk about black box and stuff like that. So, but basically, here, what you can know is that you can have #expect, and then if it fails, it will continue on to the next one. And it will run that, and so on and so forth, all within that same function. This is true also if you have many different functions that are tests. If you tell Xcode to run all of your tests, it will run all of your tests and check the expectations within every single test function, and, you know, basically tell you, hey, you know, this expectation and this expectation passed, but this one failed, right? So that's multiple expectations. Lastly, you can have throwing expectations. We talked about this before, or I briefly mentioned it before, earlier, where you can expect for a function to throw. Now, my example here is poor because I'm going to put the throw inside of the subtraction function, which is a bad choice because during the arithmetic calculator assignment, you actually were asked to put a throwing function inside of the division function, or you were asked to make the division function throw if the user passed in a 0 as the number that goes, you know, the quotient, I think, the divisor. I don't remember which one it is. Quotient. I think it's, I don't remember. Anyway, so apologies for the poor example here. We're just going to put it into subtraction because that's what I had for the second one, and I didn't have time to really go back and fix it to be division. But let's say that we want our subtraction function to only handle values that are greater than 0. Okay, so if the left-hand side minus the right-hand side ends up being less than 0, then we will throw an error. And that's just how we're writing our calculator. Deal with it, man. Okay, our calculator's cool, and it doesn't do we lost the one, just the one. Oh, it sounds like it's rebooting. The one screen just died. All the others are fine. Okay, it's just rebooting. Great, cool. If you guys want to slide over, you can, I suppose. Android. Yeah, that's the problem. It's an Android television, right? If these were tvOS, you know, if they were Apple TVs, this wouldn't be an issue. Brand loyalty. Ugh. Okay. I don't know what it's doing now. Hey, we're back. Okay, cool. So, throwing expectations. So we now have this function that throws. Our previous test still works just fine. right? We're not actually hitting that use case, okay? 10 minus 5 is never going to be less than 0, so we don't have to worry about it, right? But if we wanted to test 5 minus 10, for example, where we say result equals try subtraction 5, 10, and pass those in, well, okay, now this is going to throw, right? So the problem is when this throws, this function, because it is marked as throws, will also just throw it further. It'll throw it further up the chain, right? And then this class, this function will fail. Or not fail, but the test will fail. And it will say, hey, we're a throwing test, right? And we failed because this threw. But in this case, we don't want the test to fail. This is desired error handling behavior, right? We want this subtraction call to throw. So how do we make sure that we handle that? Well, you could wrap it in a do, try, catch block, and then you could like do all that, you know, and then do an expectation within there. And you know, Swift basically has a way to, Swift testing has a way to do exactly that, but in much, much less boilerplate, right? And that's with the expect throws. So with expect throws, you tell it the error that you expect to be thrown, and then you pass it a closure. And within that closure, at least one of your lines needs to try. And presumably, that try will throw the error that you are expecting. So if this code block, if the closure on this expect throws call does not throw the arithmetic error less than 0, that test fails. So the expectation there fails, okay? So we're making sure that our error handling works just fine. Any questions about this syntax stuff and these kind of 3 cases of expectation? Cool. Okay. Last but not least, we have requirements. So requirements are, as I said before, that when you do a hashtag expect, if that expect fails, the code continues on, right? It carries forward and it keeps going, okay? Require does not do that. Require, if the value passed to require is false, then hashtag require throws immediately, which is why you have to mark it with a try, okay? And if the function throws, it stops execution. So you never reach any of the further expectations within the function, right? Which marks them all as failures, right? So, you know, you can use require to do an early exit from your test function if you need some result to be true before you even test anything else, okay? That's require. You probably won't use it very much, but it has its uses. Like if you are doing a test on something that could be nil, that's optional, right? And your tests will all only pass if it is not optional, right? Then you can have a require at the very beginning that the value is in fact not optional. And if it is optional, if it's nil, then you can just exit the function early and say, hey, we're not going to bother testing any of this stuff because it won't pass. They won't succeed. So we can just leave early, right? Cool. The other thing to note about tests in Swift testing, because they're marked async, every single test function runs asynchronously and concurrently. So they all run at the same time, okay? This shouldn't be a problem if you are in Swift 6 language mode and you are using concurrency domains and actors and static concurrency checking to make sure that your code that you're testing is thread safe, right? Shouldn't be a problem. But it's entirely possible that it is a problem. If you are using a library, something you got from online, or some of Apple's libraries aren't concurrency safe still to this day. They're still working on updating them all. They just have so many. And you use those, and those get exercised by the test functions that you're calling. You might run into a situation where you have these tests that are running concurrently, and it causes a crash. And we'll look at how to fix that during the live coding section. So, cool. Oh, yeah, right, I did that. Yeah, so here, because we've changed this to result equals 1, then expectation failed. It was expecting 1, it got a 2, right? And then it just exits the function. Cool. All right, so writing good tests. The first thing to do when you start to write a test, when you sit down and you're like, you type @test func my test, right? And you create the block and everything, you set your stuff up. You make sure that your types that you're testing and everything, all your boilerplate stuff is all set up, and you finally get to like the part that you're trying to exercise, the piece of code that you're trying to run for your test, right? The first thing you want to do is verify that your test can in fact fail, okay? So first write your test as a negative. If you expect to get a 2, then, like if you actually expect to get a 2, then tell it that you expect a 0 and make sure that it fails, okay? This is one of those really weird edge case things where sometimes some functions that you go to write the test on can kind of somehow always pass whatever you're trying to test, right? Like for example, if you set some variable and you pass that variable into the function, and then you check to see if what you got back from the return is some change to that variable or something like that. If that variable is actually an instance of a reference type that was getting modified by the function, then the check that you do in your expectation is always going to return true, right? So first, make sure that you can make it fail, right? That's the first step. Make sure you can force a failure if you want it to fail, right? That's the first thing you do. Then fix the failure so that it passes. Make sure then it actually passes after you've verified it can fail. Again, you're writing your test and you just make the change and you're like, cool, okay, it fails. Now let me make it the number I expect. And then you run it and you see, okay, cool, it passes. If you want to write a good test, it can be helpful to try and build the test blind. So try to not look into the function that you are testing. Try not to look at its implementation at the same time. Have your tests in a different file. Write them as if you were someone using this API for the first time, right? Try to write it in a way where I would expect this API to behave in a particular way because of how it's written, because of what the names of the functions are and what their return types are. Oh, cool, it says divide, and I can pass it 2 numbers, and it gives me 1 back. I would expect that the left-hand side number and the right-hand side number are the divisor and dividend. I don't know why I keep trying to use this example because I can't remember the correct terms, but the top and the bottom of the division line, right? That's what a user expects, right? But for whatever reason, you may have written your code in a different way, where the right hand, the second parameter is actually what's on top, and the first parameter is what's on bottom. Maybe that made sense for you. Who knows, right? It depends. So try to look at your API and the functions that you're testing with fresh eyes as you're doing it in a test. You'll find this a lot easier to do than when you're in your code trying to get something done. If you're just writing a test purely focused on just making sure that the function works correctly, rather than trying to use the function in order to fulfill a requirement that your professor put into your final project that's driving you insane, right? It's a little bit easier to do it with a clear head with tests. The other thing is to make sure that you're testing useful things. You saw in the very beginning, I had a test that checked if 1 + 1 = 2. That is a valid test that compiles, okay? Swift is not going to yell at you. It's not going to give you any warnings. It's not going to say, hey, why? Right? Swift doesn't do that. They don't check to make sure you're writing useful tests. So you want to make sure that the tests you write are actually helpful, they're actually useful. you can go down a really, really deep, dark rabbit hole of trying to make sure that you're covering every single possible thing that your code could do with your tests. And if you do that, you know, you end up with falling into the trap of code coverage. Code coverage is a concept that has been around for a hot second. And basically, it is a number. And that number is the percent of lines of code in your app or library that have been exercised and run by your tests, okay? So it tells you, oh, cool, you've written 100 lines of code. And then after you run all of your tests, it says, okay, well, during these tests, we hit 50 lines of code. So your code coverage is 50%. Good job, you get an F, go home, right? That's what it feels like. We've all been students in a system where, you know, if you want to have a good grade, you need to be at 80% or higher, right? So a lot of people, when they look at code coverage, think, wow, man, I really hope my code coverage is at 80% or higher. They run the tests, they look at the code coverage, it's at 32%. They're like, I need to fix this. And they go and they start fixing it, right? Right, okay, I covered that. The test platform reads which lines are hit. It calculates the ratio against total lines. Yeah, it can be helpful, but here they would be monsters, right? So the problem is that this number, right, this percent number, we can get very fixated on it as developers. We love to improve numbers, metrics, right? Things that we can make better, right? We can look at a number and say, oh, well, if I add more tests, that number goes up, right? I can improve my code base by 3% by going from 79% code coverage to 82% code coverage. And that's so easy. Look, we have a whole function over here that's not even being exercised. If I just do that, we get 50 more lines of code covered. Great, right? And it's not exactly wrong, right? But there's an issue. And there's a kind of semi-famous quote that has been misquoted and changed and messed around with for a long time. It was first coined, I think, in the 70s, which is that it's called Goodhart's Law. And the quote is, when a measure becomes a target, it ceases to be a good measure. This is an adage that you should internalize early on in your software engineering career or software development, or, you know, really honestly, any sort of career that involves like numbers. Because this quote came from an accountant, right? It came from an economist first. They were talking about the economy in, I think, Britain, and how they were trying to target particular things. And this has been kind of proven to be true time and time again. As soon as you start as an organization, right, or even as a person, but as an organization, you start to use a metric or a measure, something where you're tracking, you know, be it ability or test scores or code coverage, right? And that you say, okay, cool, well, this number's good. Glad we have this information, it's helpful, but let's pump those numbers up. Those are rookie numbers, right? Let's get those numbers up, okay? So let's go from 62% coverage, let's get over 80% coverage. That's a B minus, we feel good about that, right? You start to run into a lot of issues, okay? Basically, sometimes it just does not make sense for a given code base to target an arbitrary number for code coverage, right? Sometimes the way that your code is, the way it has to be for the project you're working on, there's just really no reason to be writing 80% code coverage unit tests, right? You should absolutely cover the most important parts and the useful parts of your code, the things that you are adding value with, the things that your users are actually going to utilize, right? But when it comes to what you know, when it comes to just saying, hey, we want to be at 75% or higher in code coverage, like that's a goal, right? It's very, very common in industry. You're going to see it a lot. In fact, some people even make it a part of their continuous integration and continuous deployment pipelines so that you can't check code into the repository if you reduce code coverage by a certain amount. So if you add a bunch of code that's not under test, then it won't even let you check your code in, right? Those aren't bad ideas necessarily, right? Saying, hey, don't reduce our number, right? That's not bad. Saying don't reduce it below a threshold, well, okay, that means as soon as there's any give, someone's going to commit something that just barely gets you back down to the threshold until someone else adds a higher rate thing, and then it'll come back down. It'll just waffle between, right? So it gets very complicated very fast. What I will give you is a set of best practices for when you're using code coverage and understanding how to use it as an engineer. Again, you will find many organizations in industry don't follow these best practices. I would not recommend that you say anything to anyone about it when you join. They'll be like, well, this person's a problem. Don't make the mistakes I have made in my career. I'm very loud, as you all know, and I can be obnoxious when I join a place and look at their engineering practices and have things I disagree with. I will usually say them plainly, and a lot of people don't always appreciate that. So don't be like me, but use these best practices for yourself and when you have the freedom and autonomy to do so. First, do not try to get to 100% test coverage. That way lies madness. It's almost completely impossible. You can, if you try really, really, really hard, get to 95% coverage, but getting to 100% it's like, what's that thing called? Asymptotic log? It's like a logarithmic function, right? You can continuously asymptotically approach a number and it's just really hard to get there. It takes more and more time, right? So don't set a particular target either. Again, just don't say, oh, 80% is my goal. Don't have goals, right? Instead, use the coverage as a hashtag goals, right? Oh, cool. You know, we're at 60%. It would be great if we could make that better, right? Don't put numbers on it, okay? Even though it's about numbers, right? Make it aspirational, something that you can aspire to. You'll probably never reach any of your hashtag goals, or you'll reach them in some particular way that's caveated in some ways. And to be clear, I'm talking about code coverage. I'm sure you will all reach your hashtag goals in life, okay? But in code coverage, you'll never reach those goals. So aspire to them, but do not strive for them. Or strive, but you know, don't push yourself. Don't kill yourself to do it. Because as you get higher, as your code coverage increases, as you go from 60 to 70 to 80 to 90 to 95 to 97 to 98 to 99.9 to 99.99999, you get diminishing returns. The more effort that you put in, the less you get back, okay? Having 50% code coverage is infinitely better than 0%. Be very pleased with that. That's an infinite percent improvement. Going from 50 to 60 is only 10. That's just math. You can tell I'm really good at math, right? Okay, cool. Code coverage is best used not as a target for numbers, but to help you understand when you're looking at a piece of code that has a bug or that you're running into an issue with, and you look at that code and you're like, is this tested? Do we have any tests running through this and making sure it actually does what we think it does? Code coverage gives you a very fast answer of yes or no. And that's what it's useful for. Adding on this like, you know, oh, calculate how many lines of code get covered by code coverage and how many don't. Like that was added on later by managers and PMs and stuff. The original implementation of code coverage was specifically just so that engineers could know when looking at any given line of code, hey, did we test this with a unit test? Did we automate this? Or have we been just doing this manually? Sometimes the answer is, yeah, we've been doing it manually and that's the only way to do it. Or yeah, we've been doing it manually and that's fine because we barely hit this, or so on and so forth, right? But sometimes the answer is, no, yeah, we've been doing it manually and we really should automate this. Let's go ahead and do it now, right? And that's what code coverage is for. So, a little bit of a diversion into the code coverage topic, but it is just terribly, terribly important to know. Okay, we're gonna do a 10-minute break, and then I'll pull up like Xcode and we'll do some live testing code stuff. So, cool. Oh, there's audio